Alright, so in this lab what we would do is we would take some various transition metals and add ligands to them, look at some of the color changes, and write the complex ions, write the formulas for the complex ions that are produced, right? So we're going to go through these in no particular order. Let's start here with the copper. So our solution of copper, our source of copper rather, is copper sulfate pentahydrate. That's our source of copper 2 ion. If you look at this stuff, it's kind of crystalline, definitely bluish in color. Alright, so what we've got here is I've got some 5 test tubes. I've already added a little bit of copper sulfate to each of the tubes. Alright, so the first one, what we're going to do is add some water to it. About maybe 10 drops of water to it. Shake it up to try to get it dissolved up. And you see that the solution is probably pale blue in color, about the same color as the copper sulfate itself, just diluted down some. Now copper is weird in a couple of ways. The hexaalkyl ion, which is what we're forming when we dissolve it up in water, hexaalkyl ion, is not a perfect octahedron. It's distorted octahedral. 2 of the bonds are definitely longer than the other 2. Another thing is that the color of this is pretty pale compared to other complex ions. There's a reason for this, in that the center of the absorption is really on the tail end of the visible. So for example, your absorption spectrum probably looks something, this is an approximation, but your absorption spectrum looks like this. Your visible spectrum goes from 750 nanometers down to 400. Your absorption spectrum on this compound looks something like this. It's really on the tail end of the visible. So only a portion of it trails into the visible region. Biggest part of the absorption is in the infrared. Big wavelengths longer than 750. That's why the color is pale. So that's a couple of weird things about copper. So the next solution that we're going to add is the 15 molar ammonia. So instead of adding water, we have another test tube. So instead of adding the water, we're going to add 15 molar ammonia. Alright. And now you see right away that this looks a lot different. This looks a lot different than when the compound was dissolved up in water. Not only is the color different, it's much more intense. Alright, and one of the differences is that ammonia is a stronger field ligand. What we're doing is we're opening up the field splitting, we're shifting this down, we're shifting this absorption down so a bigger portion of it lies in the visible region. That's why the color becomes more intense. And we're also shifting the absorption center down so the color is actually different. So 2 things going on there. The color is more intense and the color is also shifts to a different color blue. Now, here's another way that copper is weird, and that it only changes out 4 of the water molecules. It hangs on to 2 of those water molecules, so it's not a hexamine that's produced, it's rather a tetramine. Okay? To the third tube, we're going to add some ethylene diamine, 25% ethylene diamine. Alright, so it does something similar with the ethylene diamine. The field splitting is even bigger for the ethylene diamine, meaning it's going to shift it down a little bit more. The color is actually probably more of a violet than a blue. To the fourth tube, we're going to add concentrated hydrochloric acid. And now you see it doing something different, definitely forming a yellowish colored solution. Alright, in this case it is the tetrachlorocuprate ion that's being produced. Alright, and then in the very last tube we were going to add some solution of sodium nitrite. Which forms the tetranitro. That gives you a green colored solution. Alright, so one more time. Dissolved up in water, you get the hexaquo ion, that's pale blue in color. In ammonia, you form the tetramine, which is a little bit darker shade of blue. Ethylene diamine, you get the best ethylene diamine compound, that's more of a purple color. The tetrachlorocuprate is yellow, and the tetranitro is green. Alright, so next let's go on and take a look at iron 2 ion. Okay, now our source of iron 2 ion, is going to be ferrous sulfate, FeSO4, ferrous sulfate heptahydrate, .7H2O. I don't know how well this shows up in the photo, but you can see this is kind of, color is very pale. It's almost kind of a sea green color. But anyway, our source of the iron 2 ion is ferrous sulfate heptahydrate. Alright, so this first tube, I will simply add some water to it. Alright, and you're going to see that that really doesn't, not a whole lot happening here. No big color change. Basically, you're just dissolving it up in water. In fact, the solution would have to be pretty concentrated for you to be able to tell that it is colored at all. Alright. Now, the next one, the second one, we're going to dissolve it up in water. Okay. And we're going to add just a little bit of 110 phenandroline. Alright, so just a tiny little bit. It's a small little crystals. And you see a pretty big color change to this orange-red complex ion. Alright, so that's basically forming the tris 110 phenandroline compound. That's the only two that we're going to look at for iron 2. Alright, so now we'll go on to iron 3. Now, our source of iron 3 is going to be iron 3 nitrate nonahydrate. That's our source of iron 3. Ferric nitrate with 9 waters nonahydrate. If you look at this, I don't know how well this shows up probably not too well, but it's kind of ideally this thing is kind of a pale violet color. Alright, so let's look at what happens. Again, I've already added this to the test tube. So let's look at what happens when we dissolve this up in water. Alright. Now for this one, we see a color change. We dissolve it up in water. It dissolves up to form this definitely kind of a rust yellow colored solution. But it is not the hexaalkyl that's being produced. It might perhaps start out as the hexaalkyl, but that's not the final ion. What's really being produced is this compound that has the 5 waters and 1 hydroxide. So the charge on the whole complex ion comes down from 3 plus down to 2 plus, right? Because hydroxide is a -1. So what's going on here? So it starts out as this hexaalkyl ion. And it's not just iron 3 that does this. It's lots of +3 ions because you have an exceptionally high charge density. What happens is that the bond from the iron to the oxygen becomes so strong that it polarizes the OH bonds. In other words, one of the OH bonds gets weakened. This bond becomes so strong that one of the OH bonds is broken, and eventually the H plus ion pops off. That's how you're forming the hydroxide. If you go in and test a solution like this, you would find the solution to be acidic because of this reaction. Alright, so let's take a second tube. Okay, let's take a second tube, and now we're going to add some 0.1 molar, not terribly concentrated. We're going to add some 0.1 molar thiocyanate ion. Alright, and we see this blood red color precipitate. Okay, this is basically the qualitative test for iron 3. Just like phenanthroline, 1,10-phenanthroline was the qualitative test for iron 2. This is a test for iron 3. You sometimes see this formula written FeSCN2+ without the waters. But the real formula, what's really being formed, including the waters, is FeH2O5 SCN2+. Notice we're only replacing one of the water molecules. Alright, so to this very last one, what we're going to add is some potassium ferrocyanide. Right? Now, potassium ferrocyanide is an iron 2 compound. Right? If cyanide is -6, okay, if this thing is a 4- ion, if cyanide is a -6, that means the iron is in a +2 oxidation state. So we have ferric ion here, and we're mixing it with an iron 2 compound. Alright, and we'll see what happens when we do this. Alright. Now we see this blue, very dark blue colored precipitate. If you look at this, there's definitely a precipitate in there. It's not a transparent solution that you can see through, and it's not just the color being dark. There's a precipitate in there. That is the Prussian blue precipitate, which is incidentally the same blue dye that's used in the blueprint process to make blueprint paper. It's also used as a bluing agent in laundry detergent. So how did I get this formula? Right, because we have a precipitate here, because we are producing a precipitate, we can't write a formula with a charge. A precipitate can't be a charge. A precipitate has to be a neutral compound. So the question then becomes, how do we write a neutral compound between a -4 ion and a +3 cation? You guys have done this sort of thing before when you've written formulas for ionic compounds involving polyatomic ions. For example, I'll give you an example. No, I won't. But anyway, so how do we get a neutral compound here? The only way to get the charge to balance is to have 4 of these and 3 of these, right? Because 4 times 3 is equal to 3 times 4. So we have, one more time, we have 4 of these and 3 of these, because 4 times 3 is equal to 3 times 4, right? 12 and 12. So formula is Fe4, then in brackets FeCN6, 3. Just think of this as a polyatomic ion as being no different than, let's say, a sulfate or a carbonate or phosphate. Just think of this as a polyatomic ion. Your formula that you write has to represent a complete species. It has to be electrically neutral. Alright, so next we'll go in and we'll take a look at nickel. Alright, so our source of nickel ion is nickel chloride hexahydrate. Alright, that's our source of nickel ion. So we have this greenish, forget the green label, it matches, but the green color is also coming from the solid. Alright, so nickel chloride hexahydrate, that's our source of nickel too. So we're going to do the same thing. We've got some test tubes here. Alright, so you can see, okay, here's a green solid, the bottom of the test tube. Let's dissolve that up in water. Alright, and big surprise, the green, no real color change when we dissolve it up in water, because it was basically the hexaalkyl ion in the solid state. So dissolving it up in water doesn't really change the color. Alright, so that's the hexaalkyl ion. That's green in color. Alright, to the next one, what are we going to add? We're going to add some 15 molar NH3. We're going to jack up the ammonia concentration. Alright. Now you see we're getting a much different color produced, because what we're producing is the hexamine. Right, so the hexaalkyl is green, hexamine is violet in color. Okay? Then we'll do the same thing with the ethylene diamine, 25% ethylene diamine, dissolve it up. Alright, so now we get colors a little bit different than for the ammonia. This is the ammonia colored solution was kind of almost, well, they're both violet, but this one is more, the ethylene diamine is more violet. Now the last one, what we're going to do is add dimethylglyoxime, a solution of dimethylglyoxime. Let's first dissolve this up in a little bit of water. Alright, add a few drops of water, dissolve up the nickel. And now watch this, because you're going to see a big change here. The nickel we add a couple of drops of this DMG, and bam, you get this, you know, red, pink, cherry red colored precipitate. Now notice, like I said, notice I said precipitate. It's precipitate. If you look at the sides of the test tube here, you've definitely got solid being produced. Okay, so whatever's being produced has to be a neutral compound. It's not a charged species. It's insoluble. It's precipitating out. So dimethylgloxime is actually a 1 ion. It forms a square planar compound. The dimethylgloxime is a 1 ion. Two of them coordinate to the nickel. The charge on the ligands balances the charge on the metal. Notice there's no charge. There's no charge out here. There's no charge here, and there's no counter ions in the front or the back. The charge on the ligands balances the charge on the metal. That's why it precipitates out. DMG is dimethylgloxime. Now, obviously, you can use this for a qualitative test for nickel, but this is also used as a quantitative test for nickel. If you wanted to know how much nickel was in a compound, you could precipitate it out as the DMG, dry it, weigh it, and figure out how much nickel was in your sample. Okay? There's really only one more left here, and that is the cobalt. Alright, so our source of cobalt is this cobalt chloride hexahydrate, alright, which is kind of if you look at the original bottle here, cobalt chloride hexahydrate, kind of almost purplish in color. Alright, so same as before. First thing we're going to do is dissolve it up in water. Alright, dissolve it up in water. And what are we producing? We're kind of producing a pink colored solution that's not that different than the color of the solid. It's just a little bit lighter in color. Alright, so we'll take the next one, test tube number 2, dissolve it up in some hydrochloric acid, and now what you see looks completely different. Okay, what's being produced here is the tetrachlorocobaltate ion, tetrachlorocobaltate. Definitely an intense blue color. And note also that this is a tetrahedral compound, right? Because there's only four ligands. 6 here, this is octahedral. Okay, this is tetrahedral. Alright. No precipitate. If we shook this long enough, it'll eventually all go into solution. No precipitate here. Alright. So very similar is we're going to add some saturated potassium thiocyanate. So we know we get something that is somewhat similar, but this is definitely much more of a violet color than a blue. Okay. Now I should also note, well, we'll come back to that. So this very last one here, what we're going to do is we're going to add some ethylene diamine to this. I'm sorry, not ethylene diamine, ethanol. We're going to attempt to dissolve this up in ethanol. It'll be somewhat soluble. I doubt it will completely dissolve. But if we shake it up enough, we can get some of it into solution, and it's forming a blue-colored solution, somewhat similar to what we got up here with the tetrachlorocobaltate. What we're probably producing here, we don't have enough chloride When we dissolved it up in HCl, 12 molar HCl, there was a huge amount of chloride floating around in solution. It formed the tetrachloroion. Here, we don't have that excess of chloride. All we had in the solution was the chloride that was part of the initial compound. So we don't have enough chloride to form the tetrachlorocobaltate. But there's something similar going on here as to what was going on here. What we're probably producing is forming the anhydrous cobalt chloride. Now I should add that basically you can interconvert between these. In other words, the metal will grab a hold of whatever is present in solution in excess. When we dissolved it up in water, we got the pink ion, the hexaaquo. We dissolved it up in water, we got the tetrachloro, and in the thiocyanate, we formed the tetrathiocyanado, which is violet. But we could shift this tetrachlorocobaltate, we could shift this over to the hexaaquo just by diluting it down. Right, so if I take this to tetrachlorocobaltate, that's the one we added the HCl to. Look what happens when you add water to it. Should be turning pink. Yeah, see, there we go, right? Because we've now added water to it. We've added enough water to sort of drown out the chloride ion. Now the water is present in excess, so it turns blue. We could shift it back to the blue color just by adding more HCl, right? So we can shift back and forth between these depending upon what's present in excess in solution. We could take the same thing with the ethanol one that we did down here, the one that had ethanol. We dissolved it up in ethanol, add water to it, and it'll turn pink and form the hexaaquo. Right, so one more time, the hexaaquo ion is pink. That's what you're going to get when you dissolve a cobalt-2 salt up in water. The tetrachlorocobaltate is blue. That's a tetrahedral ion. The tetrathiocyanado is violet. That's another tetrahedral ion. And then you have the anhydrous cobalt chloride. Now, we can say something from this last example. We can say something about the spectrochemical series, right? If we look at these last two compounds, they're both cobalt-2 compounds, and they're both tetrahedral. The tetrachlorocobaltate is blue, the tetrathiocyanado is violet. Now, if you go back and look, a solution that appears blue is not absorbing blue, it's absorbing orange. Blue and orange are complementary. Take the 6 colors and go around them on a color wheel. Blue and orange are opposite. If you're blue, you're absorbing orange. If you're violet, you're absorbing yellow. Violet and yellow are complementary. Does this support the spectrochemical series? In other words, if we were using this as an experiment to ask the question, okay, which is producing the bigger field splitting, how would we answer that? The question becomes, which is higher energy light, orange or yellow, right? Because absorption in a compound occurs, you have the light that's coming in, you split off the energy levels, the light's coming in. Absorption occurs when the energy of the light matches the splitting of the orbitals. So the question we have to ask ourselves, which is higher energy light, orange or yellow? So we take the entire spectrum, red, orange, yellow, green, blue, and violet, right? So we're going, or as the old adage goes, Roy GBV. So as we go this way, we're going towards decreasing wavelength and increasing energy. The shorter the wavelength, the higher energy. So on the red end, we have long wavelength, lower energy light. On this end, we have short wavelength, higher energy light. So, right? So here's orange. light, and here is yellow light, which is higher energy. Well, the light is higher energy. The yellow is higher energy light. And that means then that field splitting is bigger here than it is here because higher energy light is being absorbed. Shorter wavelength light is being absorbed. Shorter wavelength equates to higher energy. So one more time, the field splitting is bigger here than it is here. And in fact, if you look at the spectrochemical series, it will show thiocyanate is being ahead of chloride. Alright, so one more thing that I want to look at real quick that I realize I skipped over one, and that is copper being mixed with ferrocyanide. We're going to go back to copper for just a second. Alright, so we're going to put our copper in the tube here. We're going to put the copper in the tube, and we're going to add ferrocyanide. Here we go. Alright. So we will add ferrocyanide to this. And initially it dissolves up. And then it starts producing a precipitate. You look at the test tube, you definitely got a brownish, red colored precipitate that's not dissolving up, no matter how much you shake it. So let's go back to our copper page here. Right, so what's going on here? So we're mixing copper ion with ferrocyanide. Right? So once again, it's producing a precipitate. Once again, it's producing a precipitate like the iron 3 and the ferrocyanide did. Our formula, because we're producing a precipitate, our formula has to be neutral. It can't be charged. So the question becomes, how do we get a compound between a +2 cation and a 4- anion? The way you do that is you have 2 of these for every one of those, right? So again, one more time, just think about this thing as like a great big polyatomic ion. It's no different than a phosphate or a sulfate or a carbonate as a 4-. So to make the charge balance, we have to have 2 coppers. Our formula is Cu2 Fe Cn 6, and that is our formula. That's pretty much it. We pretty much went through this. You guys should be able to answer pretty much the questions about the lab at this point. Thank you for your attention.